are related to the magnocellular system, and the fact that the magnocellular system provides the dominant input to this dorsal pathway that controls visual, motor, and attention. I'm not going to go into any of that in any detail, but to point out that it contributes to unstable eye control and various other things that I haven't got time to go into. So first of all, the most striking piece of evidence, but albeit now still only 5 brains, I'm afraid, we must add that caveat, is this finding by Galaberda's group that there is a clear disruption of the magnocellular parts of the brain. In a control brain, we have in the thalamus, this is the lateral geniculate nucleus of the thalamus, we have clear separation of the so-called magnocellular layers and the parvocellular layers, and these are called coniocellular. Now you can see that the magnocellular cells are larger, you can tell by their larger nuclei, and they are clearly separated from the parvo cells. But in the dyslexic brains that they dissected, you can see that these cells have sort of mismigrated and mixed up with the parvo ones. And it turns out, as I say, that they're 30% smaller, and that means that they will conduct more slowly, and that's quite crucial. So we went ahead and measured the motion sensitivity, which, as I say, is an important way of measuring magnocellular sensitivity, and we found that both in adult dyslexics and in children, they need more of these dots. These dots are shown moving in all directions, and then some of the dots will move all together. So if we take the number of dots that are moving together and dilute it with dots that are moving randomly, we can get a measure of the motion sensitivity of these adults and children. You can see you need more dots if you are a adult dyslexic to move than control adults, or same in children. Now, it's very important that you have a control which shows that dyslexics are as good at what's called static sensitivity to visual form. So you can see here that there is, I can't really see it, but I think it's about there, there's a sort of rose-looking thing made of randomly orientated lines. And again, you can dilute that with more and more lines that are not randomly orientated, so that you destroy this percept. And the number of lines that have to be orientated correctly to make this rose gives you a measure of the static sensitivity, and it's actually a measure of the parvocellular system. And you can see that the dyslexics are worse at the random dot one, but they are, if anything, slightly better at the static one. And this controls for things like attention and whether or not you're encouraging them enough and things like that. So if we take a whole group of children, this is now 790 children, you plot their coherent motion, that's that random dot kinematogram measure that I told you about, against their ability to do some orthographic tests, you can see there's a clear relationship, and it accounts for something like 16% of the variance in these children's reading. So it's an important contributor, by no means the only contributor, to their ability to read. And this is a group of children, both good readers and bad readers. And you can, as I say, see that magnocellular function is a good predictor of their abilities. Now, one of the things that's really interesting is that if you can do something that actually improves the function of the magnocellular system, and one way of doing this is to wear yellow filters, you can actually improve reading. And the reason for this is that yellow actually facilitates the function of the magnocellular system. They receive from both the red and the green cones, the long and the medium wavelength codes, and not much at all from the short wavelength code. So if you provide them with yellow filters, because the pupils dilate, you actually get more red and green light than you would looking with no filters. And that actually facilitates the magnocellular system. And this shows you the filters actually cut out all the blue light, but allow all the red and most of the green in, and that is exactly the right filter to facilitate the magnocellular system. When you do that, in some children, I emphasize not all, but in some children this has a dramatic effect, and you can see this dramatic effect here in this child whose writing was appalling, but only 1 week later, after wearing yellow glasses, you can read all of that. And so that can have a dramatic effect. And so we did a randomized controlled trial at which we looked at the reading and spelling of children given or not given yellow spectacles, so that some children received a placebo and others received the yellow spectacles. And you can see there was a huge improvement in their reading, about 8 months in the 3 months that we gave them those spectacles in reading, and almost the same in spelling, compared with the placebo, where actually they went backwards. They should go up 3 months, and actually they only went up 2. But another 25% or so of the dyslexics we see benefit not from yellow, but from blue. Why on earth would that be? Well, the blue let through the blue light, and again, they cause dilatation of the pupil, because they cut down the overall amount of light, and that means the amount of blue light going into the eye increases. And this has a dramatic effect on some children. You can see it. They stopped his eyes moving, and they made everything look much clearer. And again, we did a randomized controlled trial, and we found that in this case we could increase their reading by 12 months in 3 months, and their spelling by not so much, but that's a pretty dramatic effect compared with placebo. Now, why should blue filters work? Because from what I said before, you'd thought that would cut down the activity of the magnocellular system. But in fact, what blue light does is work in a different way. It probably works by what's called the suprachiasmatic nucleus hypothalamic clock. In your hypothalamus, deep in the depths of your brain, there is a nucleus which times out your daily rhythms, the so-called brain's clock. It is a genetic clock that runs with 2 genes called per and time, period and time. And these 2 genes produce proteins that time out your daily rhythms. One of the important things they do is they wake you up each morning, but of course to do that they have to be somehow entrained to seasonal changes in daylight. So there's a set of ganglion cells in the retina called the melanopsin-containing ganglion cells, or intrinsically photosensitive ganglion cells, which are sensitive to blue light. And what they do is they then entrain the suprachiasmatic nucleus to the particular day length that you're dealing with, so that they'll wake you up earlier in summer and later in winter, for instance. So they control diurnal rhythms. And the way they do this, there's a number of ways they do it. But the one I want to concentrate on is via a link with the locus ceruleus, which is another important brainstem nucleus. They actually enhance the activity of the magnocellular system, both in the lateral geniculate nucleus and also this dorsal root that I was talking about earlier. And we know this is true because actually blue light at night will actually reduce the secretion of the night hormone, which is called melatonin. So we woke up undergraduates about 2 o'clock in the morning, if they'd actually gone to bed by that time. We woke them up in the morning and subjected them to our filters, which let through the blue light only, at 2 o'clock in the morning, and we observed a reduction in the amount of melatonin they were secreting. So that means that the blue light does do what we've just said it did. an interesting serendipitous observation was that we could actually help these children's migraine. Many dyslexics, along with their visual problems, actually suffer from headaches, particularly when reading. And we found that the blue can prevent these headaches, whereas yellow, in people who would benefit from blue, often makes the headaches worse. And again, we've got an explanation in terms of what the melanopsin-containing cells do on the vascular system, which is what's responsible for the headaches. In summary, therefore, there's a set of children who benefit from blue filters, and if you give them yellow filters, they actually do worse. So, as I was saying, you can increase their reading. In this case, it was about 4 months in 3 months. No, this is S scores, so this is equivalent to about 9 months of increase in reading age with the blue spectacles, but with yellow, they actually went backwards. Whereas another group, give them yellow, they do almost as well, a 3.5 increase in S score, but actually blue makes them worse. So one can't just say, oh, we'll give all children blue, all children yellow, because that would mix the two up and you wouldn't see the effect. So to summarize, we can show that if you have no help at all, children in 3 months are likely to improve their reading. These children with dyslexic problems will improve their reading by only about 1 month. So they're, relatively speaking, going backwards. If we give them grey placebo spectacles, on average they go back 1 month, as I showed you before. This is what's called reading recovery, which is a phonics thing that is often used in the UK. And you can see you can actually get the dyslexics who would otherwise go backwards to improve their reading by about 3 months and 3 months. But the yellow, blue, and I'm coming to this omega-3s later, do a much better job than the phonics teaching for these children. Let's be clear, it's not all children. So to summarize, I show you my favorite joke, which may be lost in Portuguese, but the Magna deficit causes many dyslexics to confuse the visual order of letters, so they misread the animal called a gnu. They would misread it as gun. I see it was rather lost in Portuguese. Now the other route for reading is this sublexical or phonological route, where you have to translate the letters into their sounds, d, spes, d, and so on. Now that route is very much dominated by the auditory system. And so I'm now going to show that there's an analogous system, the auditory system, which I call the auditory magnocellular system, but this is less accepted, so I must make it clear that this is a point of controversy still. The point here is that if you're going to tell the difference between, let's say, b and d, what you are doing is you are distinguishing between, in the case of b, just the second formant, that's the second frequency produced by your vocal tract, second highest. In the case of d, it goes up, but in the case of b, it goes down. And that frequency change is what you are detecting to tell you that you are hearing b rather than d. So what we did is we went ahead in a school in Meltham and we measured these children's auditory amplitude and frequency modulation sensitivity. That's sensitivity to changes in either the intensity of sound, the amplitude of sound, or in the frequency of sound. This shows you the frequency, and what this shows is that for a well-accepted phonological measure, which is called non-word naming or pseudo-word naming, if you measure the auditory FM threshold, that's the ability to detect changes in the frequency of sound, you see there's a negative correlation between the two. That is to say, the better your non-word reading, the better is your auditory FM threshold, i.e. the lower it is. So if you're very good at hearing these frequency modulation changes, you're very good at doing the auditory, non-word naming task. Whereas if you're very bad at that. Now, we've recently showed that actually rhythm, which is amplitude modulation of sound, teaching children rhythm, and you can go and see our poster if you're interested in this, improved reading, and this is not in dyslexics, but ordinary children around the age of 8, improved their reading more than teaching them pitch, which is frequency modulation, changes in frequency. And you can see there was quite a significant difference between the two, and that actually follows Goswami, who's been very clear that a lot of the phonological difficulties that children have may have an underlying amplitude modulation impairment. So, are there impaired auditory magnocells in dyslexia? Obviously, my suggestion is there is. These are large neurons in the auditory brainstem, which Stein for Cat 301. They have, again, Calaberda and his colleagues have shown that they have smaller magnocellular neurons in the medial geniculate nucleus, also staining for Cat 301, and they have lower frequency amplitude and lower frequency and amplitude modulation sensitivity. I've shown you that frequency and amplitude modulation sensitivity predict reading skills, and therefore I'm suggesting that dyslexics' poor phonology may partly result from impaired development of these auditory magnocells, and that musical training can actually improve this. So to summarize this part, magnocellular sensitivity seems to be a most important determinant of overall reading ability, and in fact, if you know a child's non-verbal IQ and you know their visual motion sensitivity, auditory frequency modulation sensitivity, their amplitude modulation sensitivity, you can account for 2/3 of their reading differences. So these are very important. These low-level sensory measurements, sensory skills, if you might say, are extremely important for the acquisition of reading skills. And that's very encouraging because they can be improved by training of various sorts or the use of filters, as I was showing you. Now, there's another aspect to this, and this is that the magnocellular systems also project strongly to the cerebellum. The brain's autopilot, the cerebellum, needs to receive accurate timing information in order to do its function, which is to predict what's going to happen in the future, and therefore enable you to adjust your movements precisely to the needs of the moment. And so it's been suggested that improving balance, or a UK program called Brain Gym, can actually improve reading. And lots of people say that this is nonsense, but actually I'm going to show you that there's a grain of truth in it, and I know Angela Fawcett will be happy about this, because together with her and my then postdoc, Catherine Stoodley, we showed very clearly that dyslexics have a tendency to have poor balance. This is shown here. We were measuring the actual degree of movement of the head in somebody just standing on one leg, and you can see that it's not big enough. Can't see it. Sorry. 10. Oh, brilliant. That's great. And you can see that the dyslexics have much more movement of the head, and therefore a more unstable balance, a bit like their unstable eye movements. And so Buffy McClelland, another person working with us, has tried to teach children better control of their movements. And as I said much earlier, there's an important contribution of the magnocellular system to the control of movements. What she's shown is that there's a huge effect size of teaching poor readers simply to control their movements better, particularly cross-lateral movements, which many children with dyslexic problems have real problems with. And you can see that the effect size compared with this is before the treatment, this is or the program, this is after, and you can see there's a stonking great effect size. So, to summarize, cerebellum is the brain's autopilot for timing and motor prediction, balance and skilled movements. Magnocellular systems all project to the cerebellum. It's known that cerebellar prediction properties are also used for cognition. Cerebellum is underactive in many dyslexics. Angela showed that as well. This Move for Words program that I've just shown you about improves reading, and we still have yet to show whether it's actually mediated by the cerebellum, but that's obviously the next thing to do. So I'm not going to go through this, but basically there's 4 varieties of magnocellular system: visual, auditory, motor, and actually kinesthetic magnocellular systems, which all feed into the sensory motor basis of dyslexia. So what about these magnocellular neurons? They're a system of large neurons specialized for temporal processing, as I've said. They have large, fast conduction. They all secrete the same proteoglycan, so they're the same lineage. They're found throughout the whole brain. It turns out they're very vulnerable. Their impaired M cell development has been found in all these conditions: prematurity, fetal alcohol syndrome, developmental dyslexia, developmental dyspraxia, developmental dysphasia, ADHD, autism spectrum, Williams syndrome, schizophrenia, depression even. Now, that sounds far too generalized to be specifically anything to do with dyslexia. But it turns out that all these neurodevelopmental syndromes run into each other. So most dyslexics have elements of dyspraxia, or elements of ADHD, even elements of autism. So I'm not at all surprised that there are magnocellular deficits can be found in all of them. The M-cell high dynamic sensitivity requires very high membrane flexibility, and I'm going to talk about that now in terms of the, or in a minute, in terms of the necessity for fish oils. But first, I want just to show you a bit about what we've been doing in the genetic area. We've been looking at genetic linkages and associations between dyslexia and the DNA of fathers, mothers, and of the dyslexic children. We've done this in over 500 families around Oxford and Reading, and we've also looked at 100 families from Boulder, from the unit there, Dick Olson's. And we're also involved in an EU consortium which is doing even more families at the moment. But what I want to do is to talk to you about just 2 genes that we in Oxford have actually discovered, really. The first is this one here on chromosome 6, on the short arm of chromosome 6, which is actually, we've now pinned down to this gene called KAIAA0319. And that gene is now known to be responsible for the control of development of the brain. It is very much expressed in that dorsal visuomotor root. This is what this shows here, these yellow dots, expressed in the dorsal visuomotor root that is important for, it's dominated by the Magno system and is important for the control of attention. Now, what does it do? Well, Joe Laturco and colleagues found that KAIAA0319 is important for the way in which cells migrate during the second and third trimesters of intrauterine brain growth. So as you probably know, all the nerve cells in the cerebral cortex, or almost all of them, are actually born around the cerebral ventricles, and they then migrate up to form the 6 layers of the adult cerebral cortex. And they migrate up these things called radial glial cells, and obviously they need signals to tell them when to move and when to stop. If you knock out, just locally, the KAIAA0319, which you now can do, obviously in mice, not humans, you see these cells don't migrate at all. They don't move up to form the right layers in the cerebral cortex, and they just stick there. And so this shows that KO319 is a gene that controls neuronal migration early in development. Now, there are a number of genes that are important, but what I wanted to show you is that what actually happens in the shown by Al Galaberda's studies is that the underexpression of KO319 in dyslexia, KIO319 is actually underexpressed by about 30%, so it only has 70% the potency, as it were, in many dyslexics. And the effect this has, it appears, is to promote these things called ectopias, which, as you see, are clustered around the left hemisphere, the area in the left hemisphere that's important for speech and reading. What it seems to do is to allow these things called ectopias, which are sometimes called brain warts, about 1 millimeter in size, so we're beginning to be able to catch them actually in MRI images. And what is happening is these cells that ought to be migrating and stopping just here, they disobey instructions and go on here. So it seems that in the case of underexpression, but not complete knockout of the gene, because the signals are in some sense awry, you get this migration of the over-migration of the genes. Now, there are 3 genes now known to be associated with dyslexia, which are all concerned with migration early in development, but later these same genes are now known to help to control your immune function. And the signals that these cells recognize when they are migrating are actually known now to be part of the immune system, the expression of a system called the MHC system during development. And so what happens is particularly magna cells, because they have more of these cell surface active things, including the proteoglycans I was talking about, they fail to develop properly and to successfully unite, as it were, contact with other magna cells, and they remain immunologically vulnerable. This is just to show you a recent study by Joe Laturco, not on KIO319, but on DCDC2, which is another gene in the same area of the MHC system. And what we see here is in the wild type, that's a normal mouse, following an injection of current, the cells produce lovely, well-synchronized bursts of activity, and this is in the cerebral cortex. Whereas in the DCD knockout, where the gene isn't working, you see there's no synchrony at all. And that is obviously related to the possibility that the kind of timing that you need, provided by auditory magna cells or visual magna cells, is missing in that DCD2 knockout mouse. Now, this can be related to the immune anomalies that are often found in dyslexics, and you all probably know from your dealings with dyslexics and their families that they have a lot more allergies, eczema, asthma, etc., uveitis, which is an eye disease, which are all autoimmune problems or aberrant immunology that afflict them. And so, just to be quick about this, the immune system is involved in the development of the dyslexic brain, and we have done some studies in which we've shown that there are anti-magnocellular antibodies in the serum of mothers with dyslexic children. I haven't got or many mothers with dyslexic children. I haven't got time to go into the details at the moment, since I'm sure I'm just about to hear the 2 minutes. God. Well, I'm going to have to hurry, because the next section is MCR5, which is melanocortin receptor 5. This is another gene that we have discovered, and I must emphasize that we haven't actually proven that this is the gene, but I think it's highly likely. And I'm showing you this because this is me waiting for my cod liver oil in 1949. So you can tell I'm older than I look. Now, the reason we were all given cod liver oil was this guy, Hugh Sinclair, who was my senior colleague in Magdalen College, Oxford. knew that there was a very important essential fatty acid called docosahexaenoic acid, which forms membranes and is very important for the flexibility of those membranes. We evolved with a predominantly fish diet, and this probably is one of the reasons that allowed our larger brain in relation to our size compared to, say, chimpanzees. But nowadays, only 25% of 18-year-olds eat any fish at all. We don't eat enough fish, at least in the UK. I can't say for Brazil, but I guess it's even worse in the inland of Brazil, where presumably not much fish is eaten. Our modern diet is totally appalling. We have too much of the things that are bad for us, such as too much sugar, salt, and what are called omega-6s, and not enough of omega-3s. And this is the terminal effect of the dangerous things we eat nowadays. These long-chain fatty acids, in particular docosahexaenoic acid, DHA, are very important to preserve the flexibility of the membrane, to allow the channels that allow magna cells to work fast, to open and close rapidly. Now, it's now clear that many children with neurodevelopmental problems, and I'm talking in particular of dyslexia, but also disadvantaged young offenders, as I'm coming to right at the end, have omega-3 deficiencies. They have low blood and brain omega-3 fatty acids, which we can nowadays measure. They have elevated a level of an enzyme called phospholipase A2, which takes the omega-3s out of the membrane in order to make things like resolvins and other things that require DHA, and another one called EPA. And in the last 1 minute, I'm going to show you that omega-3 fish oil supplements can actually improve magnocellular function, improve attention, improve reading, improve mood, and even violent offences. You'll all know that the gold standard for proving cause and effect is the so-called randomized controlled trial, where you randomly allocate to active treatment or placebo groups, and then anything that is different between the groups must be due to your active treatment. So my then postdoc, Alex Richardson, did a study in Durham, which is now repeated in Oxford in the so-called DULOB study, and she found that if you gave children omega-3s compared with a placebo, which was a capsule that looked and tasted just the same, neither side knowing who had got which, you could see that there was a huge increase in reading age in the children who received the omega-3s, but no significant difference from what you'd expect by normal development in 3 months in the children who received the placebo. Now, improving diet can also reduce violent criminal behaviour, and I haven't got the time to go into why omega-3s are important for avoiding social indiscretions, but here's a study done by another postdoc of mine, Bernard Gesch, who took 270 young prisoners in a young offenders institute, gave them omega-3s, vitamins and minerals, but the omega-3s, I think, are the important thing, and showed that you could actually reduce their offences. So these by chance, produced about 1 offence per 1,000 man days, both before supplementation, both the people who were later to get the active and the people who were going to get the placebo produced the same rate of offending. But then after 3 months of treatment, you see those who received the active reduced their rate of offending by a quarter for every offence, but for violent offences, almost 2/5 reduction in the amount of offending. So, take-home messages. Visual dyslexics reading can often be improved by blue or yellow filters because, in various ways, they bolster the magnocellular system. Blue often improves sleep, car sickness, and headaches as well. I haven't had time to tell you about that, but obviously if it improves diurnal rhythms, the synchrony or the entrainment to prevailing day length, then it will improve sleep as well. Auditory magnocellular function can often be improved by musical training, as I've shown you. Motor magnocellular function can often be improved by structured movement training. And magnocellular function in general can often be improved by eating oily fish or supplement capsules of DHA and EPA. So conclusions, basically I don't want to go into these in any detail, but there's fundamentally auditory, visual and motor, attentional and sequencing requirements for speech, reading, etc., as underlined by magnocellular function. Visual magnocellular function leads into orthographic representations and orthographic skills. Auditory magnocellular weakness impedes breakdown of word sounds into their phonemes, i.e. causes low phonological skill. The cerebellar involvement is probably underlies the incoordinated, clumsy movements and the way in which movement training programs can often improve reading. And I've shown you that weak magnocellular function may result from genetic vulnerability, from antibody attack, from omega-3 fatty acid deficiency, and this is all very exciting because these things can be remedied. And that, I think, is the bottom line that I want to get to you to take away with you, that you can do things about this. Once you understand what's going on, you can do something about it. But as a final thought, I do want you to be aware that dyslexia carries with it probably great talents. And here we have Rodin, Winston Churchill, Leonardo da Vinci, our own Richard Branson, Picasso, Whoopi Goldberg, all dyslexic, but all very talented. And I was absolutely flabbergasted, no, very pleased to read that, I don't know if he's going to talk to you about it, but we're going to hear about the positive side of dyslexia in about 2 lectures. Thank you very much.